Hello. In today's session, we will start discussing further ways to test whether a series will converge or diverge. And again, a series is just a summation of the terms of a certain sequence. In today's session, we will tackle two types of tests called the divergence test and the integral test. In a previous session, we discussed the convergence test, okay? And we said that if we want to test whether a series will converge or diverge, it's simply you write a series as n starts from 1 till infinity of a of n, this series. We said it must be equal, because this is the total summation. We can divide it into partial summations, and we can say it must be equal to the limit as n goes to infinity for the summation of a partial summation, so from k1 till n of a of k. Okay, and this part is the partial summation. So what you start n equal 1, so from k1 till 1, this is s1. Then n equal 2, this is will be a1 plus a2. Okay, n tends to 3. So you take partial summations s1, s2, and you create a sequence. And from this sequence, you need to create a formula, right? From this sequence of partial sums, you need to create a formula, a closed form formula for the sequence. We denoted it by Sn. Okay, and we said if the limit of this formula for the sequence of partial sums tends to a certain value, okay, we say it is convergent. Okay, that's what the convergence test is about. And we tackled two types with special types, the one called the telescoping series, okay, and one called the geometric series. And for instance, let's talk about the geometric series. In the geometric series, we say if we have the form a r n minus 1, we check only for r. If r is less than 1, the absolute value, then it converges. It makes our life easier rather than doing the limit n tends to infinity to the formula. Okay, so this is a special case called the geometric series. But in some scenarios, it would be difficult for you to create a closed form formula. Okay, so if the geometric series, if the series is not a geometric, and the convergence test is difficult for you to be performed, or it is difficult to find a formula for the sequence of partial sums, then how could you test whether a series will converge or diverge? That's why we need to introduce some other tests on this regard. Okay, so one of the other tests that you can do instead of creating a formula is do the not convergence test, which is called the divergence test. And this test says that if you want to check whether a series converges or diverges, you just get the function an, or the series, okay, you find the limit as n goes to infinity of a of n. If the limit of an as n goes to infinity doesn't exist, or exists but the value is non-zero, okay, non-zero, then definitely the series will diverges. Okay, however, if the limit as n goes to infinity gives you 0, so any value, if it doesn't exist or exists and the value is not 0, we say it is divergent. Why? Because as you see, if it is 1, then you add 2, 3 on top of each other, then the series will start to diverge. Now, if the limit of an as n goes to infinity is equal to 0, okay, here you can't say it is definitely will converge. In general, yeah, in most cases it will converge, but in some other cases it may diverge. So in this scenario, if it gives you 0, then you need to go and check for convergence and divergence by another test. So the divergence test is not enough. So you need to check whether it will converge or diverge. Okay, so the divergence test will not be sufficient enough. So in summary, the divergence test, you find the limit of an as n goes to infinity. If it gives you some value other than 0, or it doesn't exist, then definitely it's divergence and there is no need to perform any other test. However, if it gives you some value which is equal to 0, then here you need another test to check for divergence or convergence. Let's take an example for the first scenario, at which you have the series as n goes from 1 till infinity of sine of n. Okay, you need to check whether it converges or diverges. So you find the limit as n goes to infinity of sine of n. You know the sine is sinusoidal, okay? So as n goes to infinity, there is no certain value, right? It keeps fluctuating between -1 and 1. Okay, it takes some discrete values between -1 and 1. So we know there is no exact value. We say it doesn't exist, right? It doesn't exist. There is no limit for sine of n as n goes to infinity. Doesn't exist. And therefore, we say this series will diverge. Okay, by divergence test, as simple as that. However, if we take like the series 1 over n squared plus 1, okay, as n goes to 1 infinity, you find the limit as n goes to infinity of 1 over n squared plus 1. 1 over infinity, it is 0. Here you need to check whether it converges or diverges. So the divergence test is not enough. You need another test to check for that and make sure it converges or diverges. Okay, so we need a further test. There are several tests like the integral test, the ratio test, the root test, the comparison test, and many more. In today's session, we will be tackling the integral test. So this is integral test. So in the integral test, you just take the function f of n, and you check first if the series, like you have the series, you need to check whether it is convergent or divergent. Okay, so the first step, perform the divergence test. If it diverges, then there is no need to perform any test. If the limit of an as n goes to infinity is equal to 0, then you need to another test. So we will be using the integral test. So you take an as a function f of n, okay, and you check if this function f of n is positive and continuous and US, okay, and positive continuous and decreasing. Okay, you can check for decreasing, just take f prime like the derivative, and if it is negative, then you make sure it's decreasing. Then the series and the integral, this is the discrete form, summation, okay, from n1 to infinity. This is the integral, it is the summation. The integral is a summation, right? But in a continuous form for every single of n, whether n it is integer or not. In this case, it's integer, positive integer. Here we have from 1 to infinity, so you can take 1.1, 1.2, 1.3, and so on, of f of n, okay, or f of x. Okay, so then the series and the function, the integral of the function, will either both converge or diverge. Okay, but it is important here to highlight that the summation of the series not necessarily equal to the summation in the continuous form, which is the integration of the function. Okay, however, the integral test doesn't provide us with the summation. You cannot find the if it is converges, okay, then it must give you a certain value. This test doesn't give you what is this value is, okay, what is the value at which we converge. Okay, so it doesn't provide us with the summation. Let me give you an example. If you have the series n from 1 to infinity, 1 over n squared plus 1. So the first step, you apply the divergence test. The divergence test says that you find the limit as n goes to infinity of 1 over n squared plus 1. We know 1 over infinity is 0. So in this case, you eliminate the fact that it is 100% divergence. You have a 0. So either you have convergence and divergence. So the divergence test is not enough. You need another test. In this case, we will be using the integral test. So what we will be doing is to have a function of that, f of x, 1 over x squared. In order to apply the integral test, the function that you have need to be positive, need to be continuous, and need to be decreasing. So as you can see, you have a positive plus 1 up and x squared plus 1. So what, no matter what x you will be replacing with, okay, this is positive for every x. Okay, so the function is positive for all x. So the function is positive. You need to check if it's continuous. Of course, I'm talking here from 1 to infinity. So in the domain from 1, so on the domain from 1 to infinity. So if you substitute, you can substitute 1, yes, 2, 3, 4. So it is continuous in the domain of definition, which is 1 till infinity. So it is continuous. Okay, and you need to check if it's decreasing. As you can see, if you replace 1, 2, 3, the function starts to decrease. It's very clear. If it is not clear for you, you need to find the derivative of the function. Okay, so the derivative of 1 is 0 multiplied by this, minus the derivative of x squared is 2x multiplied by 1. Okay, over x squared plus 1 all squared. You need to find for what values of x the derivative is negative. Okay, at which the function therefore is decreasing. Okay, so it is negative, so you can cross multiply. You have minus 2x less than 0. Therefore, you have multiply all by minus 1. You have 2x greater than 0, x greater than 0. So the function is decreasing for any value, for any x greater than 0. Therefore, it is decreasing in 1 and decreasing on 1 till infinity. Okay, so the function is positive, it is continuous, and it's decreasing in the domain from 1 to infinity. Therefore, you need to apply the integral test. Okay, the integral of 1 over x squared plus 1 from 1 till infinity. Okay, so because this is improper to integrate from 1 to infinity, we used to have from constant to constant. You can replace this infinity by some constant p, let's say, and you find the limit as b goes to infinity from 1 to b. It's easier for you to do. Okay, this is the x. Okay, great. Now, if you want to perform this integration, you need to refer to the table of inverse trigonometries, and you know that the integral of 1 over u squared plus 1 du by dx is tan inverse of x, right? If you refer to the table. If you forgot about that, then you need to convert this. I mean, you cannot use substitution. 2x is not the derivative of 1, and so on. You cannot use partial division. If you have -1, you can use partial division and so on. But in this case, you cannot apply those methods of integration. So the only method is to use trigonometric substitution, right? Okay, of course, it is better to refer to the table. Okay, if you forgot the table and you need to obtain the answer, then you can do it very simply. Okay, so you need the integral of 1 over x squared plus 1 dx. You convert this x squared plus 1 into, you know, this x squared plus 1, you convert it into some triangle. Okay, x squared plus 1. Okay, this is the okay, you can, because it's positive, you know the hypotenuse is positive, right? This is x squared plus 1. You know the hypotenuse is equal radical a squared plus b squared, right? Those two sides. So this side square plus this side square gives you this side square. Okay. So you can write radical and put for the radical a square. Okay, it's the same. Okay, in this case you have this side must be equal to either x or 1. Okay, because I want to restrict myself to the tangent, secant and sine, so it's better for me to put the x here and 1. So this is correct, right? You say 1 square plus x square. Okay, it is the hypotenuse. So the hypotenuse is equal to this square plus this square, right? So tangent of theta is equal to x over 1. So you can replace x with tan theta. Okay, so this is 1 over tangent theta square plus 1. Of course, I can't integrate tangent theta square with respect to dx. So I need to replace dx with d theta, so I derive both sides. So derivative of tangent theta by dx equal dx by dx. Derivative of tangent theta is secant theta square d theta by dx equal 1. Therefore, dx can be replaced by secant square theta d theta. Okay, so this is secant square d theta. And you know that tangent square theta plus 1 is equal to secant square. I mean, you can do it, right? Plus 1, you can replace tangent with sine over cosine plus 1. Therefore, you have sine plus cosine square over cosine. You know sine plus cosine is 1. 1 over cosine is secant. And you have square, so it is square. So this is equal to the integral of 1 over secant square theta secant square theta d theta. You can cancel this one. So what is the integral of 1? It is theta, right? Theta. We started with x, we should end up with x. Of course, here you have plus some constant, not necessary in this case. So we started with x, we need to replace theta. What is theta? From this you can find theta, it is tan inverse of x. Right? This is tangent inverse of x. So the integral of 1 over x squared plus 1 is tangent inverse of x. Great. Let me create some space here. Okay, so I advise you to look over the table. It's easier to look over the table. Okay. So we know the integral of 1 over x squared as b goes to infinity is tangent inverse of x from 1 to b. So it is equal to the limit b goes to infinity. You substitute, you write the function and you substitute with b, minus, you write the function, you substitute by 1. So tan inverse, you replace x with b, minus, you write the equation and you replace x with 1. So if we draw the tangent inverse, right, we know it is the asymptote. Here you have pi over 2. So the limit as for tan inverse, this is tan inverse. So the limit as it goes, the x goes to infinity, okay, it is limit will be pi over 2. You have an asymptote. Okay, so it is pi over 2. As you go to the infinity, the tan inverse tends to be pi over 2. Okay, so tan inverse of infinity, okay, is pi over 2. Okay, so the limit p goes to infinity. If you replace infinity, it is pi over 2. The limit as b goes to infinity of a constant is constant. And what is the tan inverse of 1? Is pi over 4. Right? So the final value is pi over 4. So the integration of this function, which is continuous, positive, and decreasing, yield a certain value. So it converges to pi over 4. So we know this function converges. Okay. If the function converges, then the series will converge, because both will converge or either diverge. So the series will converge. But it doesn't indicate that the summation, the total summation, or this series, the final value will be pi over 4. Okay, it doesn't provide you with the final answer, the summation. Okay, so we know the series, this one, diverges. Converges. Okay, let's take another example. If you are given a series, let me write it. Okay, 3 over 2 and minus 1. So you have this series and you need to check if it is convergent or divergent. Okay, so the first integral test, you check for divergence test. You find the limit. Okay, divergence test, limit as n goes to infinity to 3 over 2 n minus 1. 3 over infinity is 0. So the divergence test is not enough. Okay, you need to use a further test. In this case, we will be using the integral test. So we will create a function f of x, 3 over 2x minus 1. In order to perform the integral test, this function must be continuous and positive and decreasing in the domain from 1 to infinity. So x must be from 1 to infinity. So you should check in the domain from 1 to infinity if it is positive, decreasing, and continuous. So if you replace x with 1, 2, 3, 4, 5, and so on, you know that the function is positive. So 2x minus 1 is positive for any x greater than half. And you need from 1 to infinity, therefore it is positive for every x between 1 and infinity. So it is positive. It is positive. You need to check if it is continuous. There is no limitation. You know that the denominator must be different from 0. X must be different from half. So you have a condition at x, or a discontinuity at x equal half. Okay, it must not be equal to half. But you are checking from 1 to infinity, so you don't care about the half. So it is continuous on other regions other than the half. Okay, continuous. And the final thing is to check for decreasing. You can replace a couple of values. You see it is, it's very clear decreasing, or you find the derivative. Derivative of 3 is 0. Derivative of 2x is 2. Okay. 2x minus 1 square. You need to check if it is a negative. Okay. As you can see, this is positive for every value of x. No matter what you replace x here, it is positive, right? And 2, 3 is some constant, so you have always negative. So you end up with 6 minus 6 over some positive value. Okay, so this is negative for every x. Therefore, this function is decreasing. As long as those three conditions are valid, you can apply the integral test. So you find the integral from 1 to infinity 3 2x minus 1 dx. Again, this is improper integral because you cannot say like I want to integrate from 1 to infinity. I can't reach infinity, so I can replace infinity with some constant b. And I say, okay, my b will go to infinity. Okay. Okay, the integral of this, simply it is ln, but to take into consideration the constant 2 and 3, okay, you can use the u substitution. So you say let u equal to x minus 1. So it's easier for you to say like the integral of 1 over u, right? It is ln u, rather than taking those 3 and some constant. Okay, then du by dx. Okay, you cannot integrate u with respect to dx, you need to replace dx with the du. 2, which is 2 du over 2 is dx. So I can replace this. This is the limit as b goes to infinity. The integral of 1 over u. And instead of dx, you have du over 2. Okay. Alright. B goes to infinity. The integral of u is ln u. Okay, here you have, you have 3 over 2. You can bring the constant outside. The integral of 1 over u is ln u. Okay, and here you have some boundary, 1b. Okay, although it is wrong to write 1b because 1 is for the x, is not for the u. Okay, so you can say k1, k2, some constants. Okay, limit as b goes to infinity, 3 over 2. We started with x, we end up with x, to x minus 1. Now it's not necessary to put the absolute. Why? We know 2x minus 1 is positive for any x greater than 1, right? So it is positive, continuous, and decreasing. It's in this domain, right? So it is positive. So you cannot. It's not necessary to have the absolute. Okay. Between 1 and b. So you can bring the constant outside. Limit as b goes to infinity. You replace b on the first step, minus, you replace 1 on the second step. 2 minus 1 is 1. Okay, so this is equal to 3 over 2. The limit as b goes to infinity. So ln infinity, 2 times infinity minus 1 is infinity. Ln of infinity is infinity, right? So the answer will be infinity. So it diverges. Then, as this integral test of the function gives me that it is diverges, then the series must diverge. The series will diverge. Okay, will diverge. As you can see from this test, the divergence test, it gives me 0. But it doesn't indicate whether it's convergence or divergence. That's why we use another test, which is the integral test, right? And we see like it gives me divergent. Okay, divergent. So this series will diverge. Okay, this will diverge. Okay, let's take another example. Ln n over n. Again, in the integral test, you create a function ln of x over x. Okay, guys, before doing the integral test, just check for divergence. If it diverges, there is no need to perform any other test. So you see the limit as n goes to infinity of ln n over n, infinity over infinity indeterminate. You apply L'Hopital rule, you have 1 over n over 1. 1 over n is, as n goes to infinity, is 0. So here the divergence test is not sufficient. We need to use another test. I will be using the integral test. Okay, so f of x is equal to ln x over x, ln x equal over x. So is it continuous? Yes, it is continuous from 1 to infinity. We know ln x is continuous and x is continuous. Okay, from 1 to infinity. So it is continuous. Is it positive? For x greater than 1, this is positive. Ln is always positive, so it is positive. Is it decreasing? Find the derivative. Derivative of ln x is 1 over x. Derivative of x, you need derivative of ln x is 1 over x multiplied by x minus derivative of x 1 multiplied by ln x over x squared. So this is 1 minus ln x over x squared. You need to find for which values this would be negative to check for its if it is decreasing or no. So cross multiply, you have less than 0, ln x negative less than 1, ln x is greater than minus 1. And this is correct, right? Ln x is always greater than minus 1, so it is positive for, so it's greater than minus 1, but this condition is therefore valid, right? Because it's negative, therefore it is decreasing. So it is decreasing in the domain from 1 to infinity. Alright, now you can apply the integral test. Okay, this is improper. You say limit as b goes to infinity, integral from 1 to b of ln x over x dx. You can use u substitution. Let u equal ln x du. That's amazing. Okay, so here you have ln u. So ln x is u. Okay, you defined ln x with u. And 1 over x dx is du. So 1 over x dx is du. The integral of u is u squared over 2 from 1 to b. You started with x, you end up with x. Okay. Again, it's not okay. It's not healthy in mathematics to say I want to integrate 1 to b and replace it with x and then use 1 to b for u, right? So those are some constants, okay? But I'm keeping them just to make things simpler. Okay, u, because I know at the end of the day I will not substitute with u. I will not substitute u with b or u with 1. I know once I resubstitute u with x, I will be substituting it with 1 and b. So u is ln x square, and this constant you can bring it outside, half, okay, from 1 to b. So half limit as b goes to infinity, ln of b square, ln square of 1, okay, which is 0. Okay, you know, as b goes to infinity, okay, as b goes to infinity, ln of b is, if you draw b, the ln function, okay, as x goes to infinity, ln goes to infinity, right? So this starts to increase further, so it is infinity. So therefore it is infinity, it is divergent. Okay, therefore if the function, the integral of the function is divergent, the series of ln n over n is divergent. Oh, I see there is a mistake here. Okay, look, minus ln x, if you get this 1 to the other side, it will become, let me correct this. Okay, minus 1. Okay, this is minus 1. Then if you multiply all of this with minus 1, this would become ln x greater than plus 1. Okay, so ln x must be greater than 1, so you need to solve for x. Okay, so you put exponential e power ln x greater than e power 1. So x must be greater than e. There is a problem. So x, okay, because here we are looking over n is an integer, positive integer, right? So e is approximately 2.7, so x is approximately greater than, must be 3. True? So x is greater than 3. So you need to check if it is from 3 till infinity. Okay, 3 till infinity. So this must be 3 till infinity. It doesn't make any difference, but just to make things correct. 3. So ln of 3, ln of 3. And you know infinity minus some constant, ln of 3 square is infinity. Okay, sorry for this mistake. Alright, so now finally, as we discussed in the convergence test on a previous session, there are a telescoping series, there is a geometric series. Here we could have like special cases called the P-series type, okay, P-series, which make our life easier, right? Because we test, those are special cases, okay, P-series. The P-series form is given as n equal to 1 over n power p, which is equal to 1 over n power 1 plus 1 over n2 plus 1 over n3, blah blah blah. Sorry, 1 over, I should replace n, right, not p. So 1 power p plus 1, 2 power p, 3 power p plus blah blah blah. Okay, so this is called the P-series type. So instead of doing the tests that we have learned so far, the convergence test, the divergence test, and the integral test, or using the geometric series or the telescoping series, so it is, if you have this form, okay, then you say it will, this series, I mean, it will always, okay, converge when n is when b is greater than 1, right? So 1 over, as you increase this number, okay, the sequence will start to decrease. It will diverge it will converge to a certain value. So this only happens once p is greater than 1. Okay, exactly greater than 1. Okay, and you know, if you want to apply, if you don't like, I mean, to figure out it is a P-series type, you can apply the integral test. You can do it by integral test. Okay, but this is easier. You just check for the power. Okay, you know this 1 over np is positive. It is positive. It is continuous. It is decreasing. Okay, you can perform the derivative. It's decreasing. Okay, on 1 to infinity. Okay, if this is x. If you want to perform the integral test. Otherwise, if you realize it's a P-series, then definitely you can say, okay, if p is greater than, then it converges. Okay, let me give you an example. If you have a series n equal to 1 till infinity, 1 over n power 2. You know this is a form of P-series. It is a P-series. Therefore, if it is a P-series, then you can check for the power. P equal 2, it is greater than 1, it converges. As simple as that. Another example. You have a series, let's say 2 or 3, okay, radical n. So you know this is the same as goes from infinity 1 over 3. Okay, so it is a P series. P is equal to 1 over 3. 1 over 3 is less than 1. It is divergent. So this series is divergent. Another example. So instead of doing the integral test or the divergent test or whatever test you want, it's simple, just look over the power if it is a P series. Okay. If you have n power minus pi, which is 3.14, you just convert it to look like a P series, 1 over n power pi. It is a P series with P equal to pi. Pi is greater than 1. It is convergent. Okay. Right. So this is the last example. You have some series from n1 to infinity, e power 1 over n square. Your job, please try to do it by your own and verify it is convergent. At the end of the day, you need to perform the integral test. This is not a P series. You need to perform integral test. I mean, you need to convert it to f of x 1 over x power 2. Then you integrate from 1 to infinity of f of x dx. The final answer will converge. Okay, converge to 1 minus 1 plus e. Okay, and therefore the series, this one, will converge. Okay, you need to verify this is correct, and you should be able to see that it is positive. X squared is positive, exponential is always positive, positive over positive, then the function is always positive. You need to show that it is continuous for x different from 0, greater than 0, and we are looking only from 1 to infinity, therefore it is continuous. And you need to verify that it is decreasing by finding the f prime of x and see if it is negative, decreasing in the domain 1 to infinity. After verifying those, you can apply the integral test, and this integration will converge to a some value, some constant. You say it converges. Okay, and if it is convergent, then the series must be convergent. Okay, thank you for watching. Okay, so but before I leave, as I said, on a previous section we talked about the convergence test. We talked about two particular cases, the geometric series and the telescoping series. In today's session we discussed the if we see that it's difficult to find the formula, closed form formula for a sequence of partial sums, so the convergence test is difficult for you, then use the divergent test or divergence test, and you verify if it is divergent by finding the limit as n goes to infinity of an. If it doesn't exist or different from 0, then you say it's divergent. If the value is equal to 0, this technique is not sufficient. Okay, you need to use a further test. One of those tests is called the integral test. But the condition in the integral test, the function you create from an must be continuous, positive, and decreasing. Otherwise, the integral test can't be used, and therefore you need another tests like the root test, the ratio test, the comparison test, and etc. Okay, at which we discuss some of those on further sessions. Thank you.